Hello everyone, I hope you are doing well. My name is Reza and I will be your instructor for this course on duality theory and the dual simplex method in operational research. I'm really excited to go into this fascinating subject with all of you. Now, you might be wondering what exactly is duality theory and why is it important in the field of the operational research? Well, duality theory provides us with a powerful framework for understanding the relationship between primal and the dual linear programming model. It allows us to explore the hidden connection between these two model formulation and gain a valuable insight into the optimization problem. Well, I will cover in this course what is the subject we will cover here. We'll cover 7 courses in this section. Let's start with the introduction. In this course, we will explore the fascinating concept of the duality and its application in optimization. We will discuss the relationship between primal and dual model, and we will discuss how they helped each other in problem solving in operational research. In section 2, we will learn the techniques and principles behind formulating the dual problem from the given primal model. In section 3, we expand our horizon. We will explore how the dual problem can be adapted for the various problem form. In section 4, we take a look at the relation between primal and dual model. We will uncover the deep connection and insight that arise from duality. This understanding will pave the way for interpreting the solution and application for both primal and dual problem. In section 5, we will discuss the powerful dual simplex method. We will go into this algorithm, which will use a duality to effectively solve the linear problem. Step by step, we will learn how to apply the dual simplex method through the example. In section 6, we will encounter the primal dual simplex method. This variant of the simplex method incorporates both prime and dual aspect, offering an even more robust approach to optimization problem solving. We will explore benefit these methods, building upon our knowledge of the dual simplex methods. Lastly, we will explore some important theory in duality. This theory provides us with a valuable insight and theoretical foundation for understanding the duality in optimization problem. Let's talk about one of the most significant discoveries in the early stage of the linear programming, duality. Every linear programming problem has a corresponding problem called a dual. The relationship between prime model and its dual have the many usage in several ways. To illustrate this fact, let's consider the following model. This is the model we use in this course. We have the maximization summation of the Cj times xj for j1 to n, and the subject to we have the one constraint summation of the ij times xj is less than or equal bii from 1 to m, and xj is non-negative variable j from 1 to n. Now let's focus on the dual problem of the model mentioned here. If we introduce the variable yi for each constraint here, we have the m yi variable. The dual model can be formulated as follows. So we just need to times bi by yi as an objective function, and the right hand side of the dual model would be coefficient of the xj in the objective function for the prime model. We will discuss in future how we can write the dual model. Before we convert the primal model into the its dual form, it's important to ensure that the objective function and constraint are in the standard form. In other words, with the primal model, we want to write the dual model. We aim to maximize the objective function while the constraint in the form of the lesser or equal. So we should have the maximization and the lesser or equal form of constraint. Let's talk about how to write a dual problem. Here are necessary steps. Step 1. If the primal model aim to maximize the objective function, we make the minimum form for the dual model. In step 2, if the constraint the primal model are lesser than or equal, then the constraint the dual model would be a greater than or equal. Each constraint the primal model corresponds to a variable in the form of the problem. And in step 4, the coefficient of the objective function in the dual model came from the number on the right hand side of the primal model. In step 5, the number on the right hand side of the constraint in the dual model are obtained from the coefficient of the objective function in the primal model. And all variables in both primal and the dual model are non-negative. This step will guide us in formulating the dual problem effectively. So we have the 6th step we should follow to write the dual model. Given an example, consider the following model. We have the 2 variable and 3 constraint. We have the maximization in the objective function and the lesser or equal constraint, and the both variable are non-negative. So how we can write the dual model? The process of creating the dual model is illustrated in this figure. If the constraints are in the form of the lesser than equal, the variable, okay, here, the constraints are in the form of the lesser or equal, so the variable are non-negative here in the dual model. And the objective function aim to maximize, we can create the dual model using as follows. So we have the less than or equal, the dual model would be positive or non-negative. If the variable of the primal model are non-negative, the form of the constraint in the dual model would be greater or equal. And if we have the maximization in the prime model, we have the minimization in the dual model. 10, 36, and 40, this is the right hand side of the prime model. This is the coefficient of the y1, y2, and y3 in the dual model. 4 and 5 is the coefficient of the x1 and x2 in the objective function of the prime model. This is the right hand side of the prime dual constraint the dual model. So let's consider dual model for the other form. If we don't have the standard formation for the primal model, if the prime model has the constraint in the form of the equality, we need to make some change. Each constraint is replaced by 2 constraints with the same variable and the coefficient, one greater than or equal to, and the other constraint are the lesser than or equal. By multiplying the greater than or equal constraint by -1, we can transform both constraints into a smaller or lesser or equal form. This modification ensures that the dual problem remains in the standard form with the primal model. So we have another example. Let's work on the example and write the dual model for the given problem. The first constraint can be converted into the can be represented by splitting into the 2 inequality. So this is the equality constraint. We can convert by 2 inequality constraint as follows. Now we can write the dual model because we have the standard form maximization lesser than or equal, and x1 and x2 is non-negative. So we can write the dual model. This is the dual model. We have the three variable for duality: y1, y2, and y3. If we represent the variable of the dual model as a y1 and y2 and y3, the dual model can be formulated here as follows. Let's make a modification of this model by introducing the y4 is equal to y1 minus y2. y4 is a free variable. Since the difference between two non-negative variables y2 and y1 can be either positive or negative, so we can express it as follows: y4 is free in sign or unrestricted. Here is a general rule to keep in mind. It's a very important rule. Whenever an equality constraint is present in the prime model, the corresponding variable in the dual model become free in sign. So this is a very important point you should consider to write the dual model. Given another example. So to create the dual model, we make a substitution for the free variable x1. We express x1 as a difference between x2 and x3. So we just change x1 to x2 minus x3. By using the above approach, we can express the dual model as follows. The first two constants can be changed. This is the dual model. This is the dual model of this model. So the first two constraints, this is this constraint and this constraint, change with an equality form. So you just need, you just need to multiply the second constraint by -1. So we have two constraints, one greater than, another one lesser than. So you can substitute these two constraints by one constraint. 2y1 plus 3y2 is equal to 3. So there is another general rule you should remember. Whenever a variable in the form of when a variable is free in sign or unrestricted in the prime model, the corresponding constraint for that variable in the dual model become an equality form. This is another important point you should consider. Let's consider the following model. Now find the solution in this model by applying the dual model. First, we write the dual model. We have the three constraints, maximization form and lesser than or equal constraint. We have the three dual variables, y1, y2, and y3. So this is the dual model. And if we solve the dual model, the optimal solution here would be here. Okay. This is the optimal solution of the dual model. This is the optimal solution of the prime model. This is the shadow price of the prime model. This is the shadow price of the dual model. If you go to the second course of the Optimization City website, we will learn over there how we can find a shadow price. This is the very important observation we should consider here. We can observe an important point known as a duality theory in operation research. The shadow price of the constraint in the primal model, is equal to the optimal value of the variable in the dual model. Similarly, the optimal value of the variable in the primal model is equal to the shadow price in the dual model. So this is a very important point that we, as a noun, is a duality theory. This is another point we should consider. I write the observation here. This is another observation we should consider. The following table provides a list of all basic solutions for both primal and dual model in this example. Looking at the above table, we notice that there is only one case where the solution of the both primal and the dual is feasible. This solution happens to be an optimal solution for both models. However, in other case, either one or both problems are infeasible. So we have only one case that this basic solution is feasible. This is the optimal solution of the both problem. This is a very important theory in the operational system, in the subject of the duality theory. The relationship between the prime and dual problem solution, which are so important, we discuss in this slide. If the prime model has a bounded optimal solution, the dual problem also have a bounded optimal solution. However, if the prime problem has unbounded solution, the dual problem is infeasible. It's possible for both problems have not to have an optimal solution, which is called infeasible, but they cannot both have the unbounded optimal solution. To summarize the different case, we can see in this slide that uh, in the right column you have the situation for prime model, and the left column you can all situation for dual problem. Let's work on an example where we make and graph a prime problem with the two decision variable and two functional constraints. This example will have feasible solution but an unbounded objective function. Then we will make the dual problem and demonstrate graphically it has no feasible solution. Let's examine the scenario where x1 and x2 is equal to c and c approach to infinity, and z, which is called the objective function, also tend to infinity. This implies that the objective function become unbounded. Now let's look at the dual problem. This is the dual problem of this prime model. In the first, we solve graphically the prime model. You can see that the prime model is unbounded because the objective function can increase infinitely in this direction. Also, we solve the dual model graphically, and we can see that there is no feasible solution, so we have infeasible model. Let's work on an example that involves the following problem. We have the two functional constraints and two variables which are non-negative. We have four parts. In part A, make the dual problem for the given prime model. In part B, we solve the prime and dual model graphically. In part C, we utilize the information from part B to create a table listing the complementary basic solution for both problems. And in part D, we solve the simplex method for prime model step by step. At each step, we find the basic feasible solution for prime and dual model. This is the dual model for the prime model. We have the two functional constraints for dual model and two variables which are non-negative. In part B, the prime optimal solution for the original model can be determined graphically as a follow. So the objective function, the optimal objective function is 45, and x star, x1 star is 2.5, and 2x star is 3.75. If we solve the dual model graphically, we have the same objective function, but y1 star is zero point 0.5 and y2 star is 3.5. Here is a list of corner point or basic solution for both prime and dual model. It's evident that only one row is feasible. This is the fourth row that feasible, that prime model and the dual model is feasible. This is the optimal solution for both problems, which are common with the last section. In this part, we use the simplex methods for solving the prime model and compare the solution of the prime and dual solution. In the initial step of the prime simplex method, the value of the basic variable for prime and dual are as follow. This is the optimal solution for prime, and this is the optimal solution for dual. So we can see that the -6 and -0 is the reduced cost, and these 2 0 is the shadow price for first or second constraint. The second step of the prime simplex method, the value of the basic variable for the prime and dual model is as follow. You can see that the dual value is still infeasible, so we are not in the optimal solution. In the third step of the simplex method, the value of the basic for both problems are feasible, so we have the optimal solution. So let's go to the dual simplex method. Dual simplex method can be seen as a mirror image of the simplex method. What does it mean? While the simplex method focuses on the prime feasible but not the prime optimal, which is called dual feasible basic solution, and move for achieving the dual feasibility. But in the dual simplex method, it deals with the basic solution in the prime model that are dual feasible, which is called prime optimal, but are not prime feasible. It then moves toward achieving the prime feasible as well as to reaching the optimal solution. So they are the mirror image. So you can, in the prime simplex method, you are going to find the prime optimal, but in the dual simplex method, you are going to find the prime feasibility. This is the different point of these two methods. The dual simplex method is used for a certain special case. Typically, it's easier to find the initial basic feasible solution rather than the dual feasible solution. However, in situations where making an initial basic feasible solution require introducing many artificial variables, it may be more convenient to start a dual feasible solution and employ the dual simplex method. As you remember, in the the second course, we discussed the method we call Big M method for solving the linear model with the artificial variable. So it's very difficult. In this case, you can use the dual simplex method. In the maximization form, the problem to be solved is as follows. To convert the problem into a standard form, you need to introduce artificial variable si, which is called slack. And here, this is the summary of the dual simplex method. In step 0, convert any constraint in the form of the greater to less form by multiplying both sides by -1, introducing the slack variable if necessary to create the equation in equality form. Find a basic solution where the coefficient in the objective function rows are 0 for basic variable and non-negative for non-basic variable. This is the basic solution. Proceed to step 1. In step 1, check if all basic solutions are non-negative. Bi is greater than 0. If they are, the solution is feasible and optimal, so stop. If there exists the Bi is less than 0, go to step 2. Follow this step in step 2. In step 2-1, determine the leaving basic variable. Choose the negative basic variable R with the largest absolute right-hand side. If all coefficients in the R rows are non-negative, here, stop. The problem is infeasible. If there exists a negative coefficient Rij is less than 0, go to step 2-2. In this step, we are finding the entering basic variable. Select the non-basic variable S with the non-negative coefficient Rij is less than 0 in that equation. Choose the variable with the smallest absolute value of the ratio of the row 0 coefficient to the coefficient of that equation. This is the test we are using. That's to find the entering basic variable. Based on the above rule, that test, enter variable S into the basic and remove the variable R from the basic. Box the row here. Box the row in front of the XR and label it the pivot row. Box the column below the variable S and label it the pivot column. The number common to boxes in column is called pivot number. In step 2-3, determine the new basic solution using the elementary row operation as follows. We do the 3 steps for the elementary row operation. Divide the pivot row by pivot number. For each other row, including row 0 with the negative coefficient in the pivot column, add to the row the product of the absolute value of this coefficient and the new pivot row. For the other row with the positive coefficient in the pivot column, subtract from the row the product of this coefficient and the new pivot variable. This is the 3rd step. Go back to step 1 and repeat the process. So go to solve the example with the dual simplex method. Here we solve the problem using the dual simplex method. First, we need to convert the constraints to the less than or equal and introduce the slack variable to equalize the constraint. Here there is an updated model we are going to solve. So you can see that we multiply the first and second constraint by -1 and add the slack variable to make the equal constraint. Start with the initial basic solution 0, 0, 0, -3, -5, which is not feasible due to the negative value of x4 and x5, which is -3 and -5. We will now apply the dual simplex method using the table below. This is a dual feasible solution or prime optimal, but not prime feasible. This is the difference between the dual simplex method and the prime simplex method. Go through each iteration. In iteration 0, here, the iteration 0, in this row, you can see we have the 3 row. First row for Z, second for X4, and second for X5. We select the X5 as an entering basic variable because -5, the absolute value of the -5 is greater than the absolute value of -3. To determine the leaving basic variable, we use the ratio test because 12 divided by -2 is less than 18 divided by -2. of course, absolute value. X2 is chosen as a leaving variable. I should mention that we do the division by negative value. So if we have the plus 2, it's not good for ratio test. It should be minus or negative value. To replace x2 with x5 as a new entering variable, we divided row 2 by minus 2. So after this operation, we have the next table. In iteration 1, we check the termination condition. Since minus 3 is not greater than 0, the current solution is not dual optimal. X4 becomes the leaving variable. Here, X4 is a leaving variable according to the minimum ratio test. 4 divided by 1 and 6 divided by 3, x3 is chosen as the entering variable here. To create a new simplex table, we divide row 1 by divided minus 3. So after this operation, we have the next table in iteration 2. We examine the solution and find it's optimal because none of the right hand side is negative. So the algorithm is finished. You can see that the optimal value for this problem is x1 is 0, x2 is 1.5, x3 is 1, and x4 and x5 is equal to 0. Let's explore another example. We have the model here with 2 variable and 3 constraint. First, we will solve the problem graphically. Second, we will manually apply the dual simplex method and solve the model. Thirdly, we will draw the paths connecting the basic solution using the dual simplex method. First, in part A, to solve the problem graphically, we can plot the constraint on the graph and find the feasible region. Then we locate the kernel point of the feasible region. We have the 3 kernel point and evaluate the objective function for 3 kernel point. The optimal solution is the kernel point with the maximum objective function, which is this point. This is the objective function, which is equal x1 is 2.5 and x2 is equal 50. So in part B, to solve the problem using the dual simplex method, we need to follow this step mentioned earlier in the context of the dual simplex method. This involves selecting entering and leaving variable, performing a row operation, updating table until the optimal solution is reached. So we have the 3 iteration. And in the last iteration, you can see that the right hand side is positive, and so we have the optimal solution. In the optimal solution, x1 is 2.5, x2 is 15, and objective function is 32.5. So in the last one, we draw the path of the connecting the basic solution through the dual simplex method. We can represent the basic solution as a point of the graph. Starting from the initial basic solution, what is the initial basic solution in the first iteration is x1 is 0, x2 is 0. So here, this is the first basic solution. What is the next? X1 is 0 and x2 is 15. So this is the next basic solution. And what is the last one? Is x1 is 2.5 and x2 is 15. So this is the last one and also the optimal solution. We are moving outside. The most important, this is a very important point in the dual simplex method. We are moving outside in the outside of the feasible region till the we are moving outside of the feasible region until reach the feasible region. So we are here, this is out of the feasible region. The next iteration is outside the feasible region, and the last one is the kernel point, which is in the feasible region. This is the difference between the dual simplex method and the prime simplex method. Next, we go forward to another algorithm for solving the LP model, which is more efficient. The prime dual simplex method is used for the problems that are both infeasible and non-optimal. Unlike the other method, it means the simplex and prime simplex and dual simplex. This algorithm does not require the addition of any artificial variable. That's very important point. It combines the concept from the prime simplex and dual simplex. Note that there is a different variation of the prime dual simplex method. We pick one of them. So what is the algorithm of the prime simplex methods? In step one, we convert the problem's constraint to the smaller or equal form and transform the objective function to maximize. In step two, we introduce the slack variable to constraint and set up the simplex methods. In step three, we calculate the effect of the objective function using either the prime simplex or dual simplex. There are two cases here. The first case is prime simplex effect. In this effect, when there is a variable with the negative coefficient in row 0 and the pivot column's number and the number on right hand side opposite that number are non-negative, we calculate the effect like this. So there is another effect, it's called dual simplex effect. When there is a variable in the row 0 with the non-negative coefficient and the pivot column number and the number of right hand side opposite that number are negative, we calculate the dual simplex effect like this. In step 4, we choose the largest absolute value calculated from the effect the prime and prime and dual simplex. As mentioned in step 2, step 3, follow the prime and dual algorithm accordingly. If neither can be applied, the process is finished. Otherwise, we return to step 3. So let's look at as an example, a very important example. We will follow the prime dual simplex methods. Follow the step 1 and 2. We transform the model accordingly. So it means we should first we multiply constraint 1 and 2 by -1 and then add the slack variable, so we have this model. Next, we calculate the prime simplex effect based on a negative coefficient of x2 in row 0, which is -6, and the present of the only positive number in this row is 5, and the positive number of right hand side is 35. The calculation is as follows. So here we have 35 as a bi here. This is a positive value, and 6 is a negative coefficient of x2 in the objective function here. This is -6. You know that you should go this part of the equation to other side of the equal, so it's very simple. So really it's -6, and 32 is 5, so it should be positive, and we add the 5 as a this part of this equation. So we have the 42 as a prime simplex methods. We also calculate dual simplex method effect, the non-negative coefficient of the x1 in row 0 here. This is the positive value. We are using this positive value for dual simplex effect. So we have 3 and 3 here, and this is the right hand side. We should be negative value, and the coefficient of the x here, x1, just behind the x1 in the objective function. So it's -1 and -3. As a matter of fact, we have the two dual simplex effects. One of them is 80 and the other is 9. Since the prime simplex effect 42 is the largest among the three effects calculated above, we will proceed with the new calculation using the prime simplex methods. So this calculation is done by the following. So we do the simplex method, prime simplex method, as we state in the beginning of the course. So S3 is a living variable, X2 is a entering variable. So we do the elementary operation and we have the this table. Okay, so in this table, we cannot calculate the simplex effect as there are no negative number in the row 0. So they're all positive. However, we can calculate the dual simplex method because we have a one negative value. Since only negative value -2 is associated with the basic variable S2, okay, and only the negative number in row 2 is -1.6, and okay, and the coefficient of this variable in the objective function is positive, we can calculate the dual simplex effect. So this effect is the only effect in this case. Is calculated as follow. Here, this is the calculation, and the dual simplex effect would be 14.25. As a matter of fact, we do the dual simplex methods. And finally, in table 3, we cannot calculate. We do the elementary operation for dual simplex method in this table. So we have the table 3. In table 3, we cannot calculate the prime simplex effect as there are no negative number in the row 0. Similarly, since our number of right-hand side are positive, we cannot calculate the dual simplex method effect, dual simplex effect either. Therefore, table 3 is optimal. So we reached the optimal solution. This is a very important figure. In this figure, you can see that the process of the prime dual simplex methods in the red line. So we do the 2 iteration to find the optimal solution. But if we follow the prime simplex method, we should do the 3 iteration, which is showing in green line. Okay, there are 2 important theory in the dual theory. First one is the weak duality theory. The weak duality theory states that for any feasible solution to the prime and dual linear program, the objective function of the prime model will always be less than or equal to the objective function of the dual model. In other words, the prime model provides a lower bound on the objective function of the dual model, which is stated here. If x1 is x1 till xn is a feasible solution of the prime model, and if y1 till ym is a feasible solution of the dual model, then we have the following definition, which is called gap duality. The difference between optimal objective function of the prime and dual is known as a gap duality. In the linear programming, there is no gap between optimal objective function value of the prime and dual model, which is referred as the strong duality gap. We will discuss another topic in the future called integer programming. We have the duality gap at that problem, which is not equal to 0. What is the strong duality theory? If the prime model has an optimal solution x1 till xn, then the dual the problem also has the optimal value yn till ym, such that the objective function of the prime model is equal to objective function of the dual model. In other words, if the prime model has the optimal solution x1 till xm, Then the dual problem also has the optimal solution of y on to yn with the same objective function, which is this theory called the strong duality theory, which is very, very common in literature of the operation research. So that's, if you are really interested in practicing more exercises related to operation research, I invite you to check out my learning website optimization, www.optimizationcity.com. There you can find a variety of resources and examples to help you deepen your understanding of the subject of the duality. Whether you are studying a linear programming, simplex method, optimization, and any topic of in the operation research, you will find plenty of exercise to challenge yourself and reinforce your knowledge. So why you not give it a try? Head over to our website and practice more. Thank you so much for watching us. If you are going to send an email or asking any question, you can send an email by optimizationcity@gmail.com, or you can fill the contact form in our website. Thank you so much for watching, and goodbye for now.